Hey, I'm Paul. I'm one of the creators of Unison. I'm going to be talking about how you can use Unison and Unison Cloud to do large-scale distributed event processing. I'm going to work my way up to explaining code like this. This is a 6-line distributed streaming MapReduce implementation. This is an example of the kind of thing that you can build with this library. So it's intended to be a very high level of abstraction. You focus just on the logic of the calculations themselves. You don't have to worry about packaging or deployment or writing, serialization and networking code. So let's get to it. All right, so here is the general problem that we're trying to solve. It is event processing. This is something that comes up in lots of organizations in various forms. You might be collecting low-level app telemetry or usage data, and you want to parse out higher-level aggregate statistics, like what were the top 5 songs by state over the last 7 days, or what have you. Another place this comes up is just any sort of application event processing, like a new user signs up, and you need to go through a series of processing stages to get the user fully added to your system, or what have you. There are two kinds of approaches that people take. So the raw events are often sent to some event store like Kafka or Kinesis. And those technologies work really well for storing events, but how do you actually define calculations or processing pipelines on top of these event streams? And what people will sometimes use, there's kind of two maybe opposite ends of the spectrum here. There is using some sort of limited query language like a KSQL or a Spark SQL. These are pretty nice if they can express what you're trying to do, but they suffer from what I call the generality cliff, in that SQL is not a general purpose programming language, and very often you need a general purpose programming language to define whatever the logic of your processing pipeline is. So just for example, you might be processing an event, and in response to that event you want to make a couple HTTP requests to some other service in parallel, and use some of the information from that HTTP call to affect how you process the event. That's the kind of thing that is super easy to do in a general purpose language and super hard or impossible to do in the middle of a SQL query. So there's kind of a reason why we don't build arbitrary application logic in SQL, and why we have general purpose programming languages for that task. Okay, so there's that kind of one end of the spectrum. The other end of the spectrum is to use a completely general purpose programming language, like Scala or Go or Rust or whatever, and just connect that up to Kafka, write pipelines or pipeline stages using that programming language. This is obviously incredibly flexible. You can define arbitrary logic in your pipeline, but it gets messy because there's just a lot of work that you end up doing that's not the actual business logic. So you need to be packaging up and deploying pipelines or pipeline stages. You often have a layer of parsing and serialization code at the boundaries between stages. And then also refactoring this implied data flow graph is not trivial. So if you want to say split a pipeline stage into 3 pipeline stages, you might be doing things like what was formerly 1 microservice now needs to be 3 different services, each of which needs to be packaged up into containers, deployed, orchestrated, operated, and so forth. Okay, so the Unison and Unison Cloud approach is different. So it's a functional library which has a single core type, the keyed log, klog kv. So conceptually, think of this as like a big distributed map from k to, for each k, we have a stream of values. Okay, and the library is concerned with operating on and transforming these k-logs in various ways. And so let me just kind of walk through some of the API here. So you can combine, given a list of k-logs, you can combine them into a single k-log. Merge together the US events and the Europe events into a single event stream. You can repartition a k-log. So given a k-log k, we can produce a k-log k2 given this partitioning function. The partitioning function can also drop keys in doing so. So you can use this to, say, group events by country or by state, or only pick out countries in North America, things like that. Okay, this next function is a sort of, this is probably the lowest level looping construct, but fundamentally you are transforming the value type of a k-log. So you're going from k-log kv to k-log kv2. And you get to do it with a stateful fold that can skip over events and also explode a single event into multiple events. You also get access to remote while you are folding. So in the middle of processing an event, you can, issue 10 HTTP requests in parallel if you want. Or in response to an event, you could spawn a big distributed computation, whatever you need to do. This function is sufficient to implement map, filter, fold, basically anything you can think of that is a causal function of a stream. So anything that computes its output at any given point only by looking at the elements that have come before can be implemented with this function. And this function is not generally used directly. Instead, we have a little DSL which ultimately compiles down to a single call to loop. I'll show that a bit later. Lastly, you may want to send the events produced by a k-log elsewhere, say publishing back to Kinesis or what have you. And so, yes, you can attach a sync to any k-log. So you'll notice there's no serialization or networking code here in this API, and all of the operations that you're doing on a k-log are sort of implicitly parallel. So you're getting parallelism in two places. So first of all, you're getting parallelism per key. So your raw events might be, say, keyed by, I don't know, user ID. And you have events coming in for each user. So if you apply a transformation to those raw events, it is implicitly operating in parallel, distributed on all of those users, all the logs for those users. Okay, so that's kind of one level of parallelism. The next level of parallelism is if you have multiple transformations, loop transformations. So transforming the V type. Those are going to be different pipeline stages. So you call loop once and do some series of transformations, and then you do that again. Those two stages can be operating in parallel as well. So sort of two levels of parallelism. Here is just some more example code. This is kind of showing a little bit more of the higher level API, so not calling loop directly. So yeah, merge US events and Europe events. You're partitioning the keys using some partitioning function. Then we are calling transform. So transform is ultimately going to make a single call to loop. It's going to create a single pipeline stages, but we get to create that pipeline stage in a nice compositional way. So we're going to do a map to get the widget count, then we're going to do a fold, then a filter, and all that's going to be fused together into a single pipeline stage and a single call to loop. So it lets you assemble these very complicated pipeline stages that would have very complicated state if they had to be written directly, but you get to assemble them in this nice compositional fashion. Okay, and then here is the distributed MapReduce implementation. Let me just walk through this a little bit. So there's kind of two different stages. So or 3 different stages. So in the first stage, we are going to take all of the keys and reduce each of the keys. So each key has a set of events, and we are reducing the log for each key. So that's this first stage: transform, map keyed, and then reduce. Then the next stage is we might have 1 million keys still at this point. Then we reduce that 1 million keys down to a much smaller number of buckets, max parallelism. Say that's 128. Reduce it to 128 buckets, then we reduce each of those buckets. Now we still have 128 buckets, we need to get a final result, and we reduce those 128 buckets down to a single bucket with another partition, and then finally reduce that down to a single value. And so now this is a streaming MapReduce implementation. So when events come in, if just one event comes in, it's going to basically propagate through those 2 stages and produce a new updated result very quickly, without having to reprocess the entire data set. Cool. So that's the gist of the programming API. I'll show a demo in a minute, but yeah, it's this nice high-level API meant to be super scalable, supporting massively parallel ingestion of data, because you can be sending data independently to different keys, and then also massively parallel distributed transformation of these keyed logs. You don't write any manual serialization code at the boundaries between stages. Really nice thing is that you can deploy new calculations in seconds. You don't do any packaging or infrastructure management. We also get exactly once delivery, so messages will not be dropped or duplicated in the middle of a processing pipeline. We can also integrate with an existing Kafka or Kinesis system, or really any other event source or sink. And kind of a nice thing that is not actually that common is for this type of approach is that we support separate deployment. So different teams can deploy new pipelines and calculations independently without necessarily having to coordinate with each other. And there is no possibility of dependency conflicts in doing so. So it's not like there's a single monolithic, pipeline that's running for like the entire organization. It's really meant to be something that different teams are empowered to define new calculations pretty easily. And yeah, this is also backed by an open source library. It's looking like it'll end up at around 2,000 lines of code, and it runs on top of Unison Cloud. Okay, so let's see a demo. How about that? Okay. This is a little word count example. So let's see. I have here, so that MapReduce function that I showed, I'm actually calling it here, okay? And I have a log, klog from text to text, maps document IDs to the document contents. Here's just like some code to send an event to a klog. So I didn't actually show that earlier, but of course you can publish events to a klog. And here's my pipeline. So I'm calling MapReduce. I'm counting the words for each document. I'm just calling text.words, getting list.size. And then the reduce function is just summation. And I am printing out the count. I'm just attaching a sink that logs to the console. Okay, so I'm going to go ahead and run this, and you'll see that when I do run this, it's going to publish the events, and you'll see like a count that gets published after each event. So the event comes in, a new count is updated, and so forth. And so yeah, that's pretty much it. So yeah, if this sounds interesting to you, feel free to shoot us an email at hello@UnisonCloud if you want to explore maybe seeing if the system could be used at your company. But yeah, hope you enjoyed.